Hello, everyone, and welcome to the latest edition of the Robson Forensic webinar series. Before we get started today, I would like to ask for there to be no recording of audio or video or taking screenshots during this webinar. The presentation and the corresponding slides are copyrighted by Robson Forensic and may not be recorded, copied, distributed, or otherwise used without authorization. With that, we will get started, and I will introduce today's presenter. Today, Marcus Mazza from our technical services group will be presenting on how to determine vehicle speed from video surveillance footage. If you have any questions during the course of the presentation, you can submit them via the Q&A button at the bottom of your Zoom window, or you can email them to us at inquiries@robsonforensic.com. And with that, I will hand it over to Marcus.
Great, thank you, Ann. So, as Ann said, my name is Marcus Mazza. I'm a mechanical engineer here at Robson Forensic and the head of our technical services group here. I spent a number of years in the automotive industry, along with the defense industry before coming here to Robson. At Robson, I started life in our crash group as a testifying expert. And in the crash group, we rely a lot on technologies such as laser scanning, CAD, photogrammetry, and video analysis in the course of our work. And here at our technical services department, we offer many of these technologies to our experts within the company here at Robson, and also on a consulting basis directly to our clients. So today specifically, we're going to be talking about video, and even more specifically, speed from video. This is something we get asked a lot when we get video evidence. And today we see more and more video evidence. In fact, it's probably more rare that we see a case without video evidence than we see a case where we do have video evidence that needs to be analyzed. And cameras are everywhere. It's amazing how many places have cameras. Cameras are becoming very small and cheap. And it's amazing how many of these incidents are caught on camera. But again, with this evidence, we need to be very careful in how we do this analysis in order to ensure that we're doing it in a forensically sound manner for the case in question. So again, cameras are everywhere. It's likely that we may be on a camera at any second and we don't even know it. So some of the places where we find this camera footage, again, we look at things like ATMs. We see doorbell cameras now. A lot of people have doorbell cameras. We've gotten quite a few cases recently where we've had doorbell camera footage. Intersection cameras. I know here in Lancaster where we live, every intersection within the city has a intersection camera. Police body cameras, obviously cell phone cameras. Almost everyone carries a cell phone now. And in fact, many of those cell phones are also being used as dash cameras within a car. Using different dash cam apps. And sometimes we don't think about, a lot of our vehicles today have integrated cameras as part of the ADAS systems or advanced driving systems. Those cameras also can record incident footage, depending on the make, model, and manufacturer of the vehicle. We may or may not be able to retrieve some of that footage as well. So, one of the things I like to stress is, if you do have a case or an incident, really kind of scour the area and make sure that all cameras are being identified and that footage is being retrieved. Again, oftentimes this video footage can be critical in analyzing a specific case. And this isn't just for car crash cases. This can be for almost any type of case. We're seeing video being used in cases across the board. Again, not just for crash. But again, today we are going to be looking at a specific case study, and that case study is going to be the speed of a vehicle recorded in the video. Again, these same analysis techniques can be used for pedestrian speed or really finding and tracking the speed of almost any object within a video frame or within video footage. So today we're going to explore two different methods, probably two of our more common methods that we use when analyzing speed from video. The first of which is called, or what I refer to as the linear perspective or line of sight method. So again, we have a camera, and a camera, light travels in a straight line, and we see here. We have a camera here depicted on the left, and we have a series of objects. And this is a top view. that are in the frame of that video. When we have two objects that fall along the same line of sight emanating from the camera, so for instance, we have a red circle that is in the same line of sight as this orange square, as drawn from the point of the camera. When we look at the actual video recording or frame from the camera, those are going to fall on top of each other. So we're going to see those as overlapping in that frame on top of each other. So anytime we look at a video and we see two objects that are on top of each other in that video, we know that although they may not be in the same position, we do know that they will fall along that same line of sight from the camera. And that's critical information that we use when positioning a vehicle or other object in our video as we do an analysis. So with that said, what we're going to be looking at today is a video taken from a surveillance camera on our own laboratory here at Robson. We have in frame here a red Ford F-150 pickup truck that's driving along the street in front of our lab. And this is footage that we captured with one of our cameras. This is our own vehicle, so we do have known speed of the vehicle that we're going to use later on to compare to see how well did our analysis compare to the actual speed of the vehicle. So again, the question here being posed is, I have this truck proceeding. What is the speed of the truck in this video? So we're going to start using our first method, the linear perspective line of sight method. And we need a little more information than just the video. So we also need to know some geometry or the layout of this area. We rely oftentimes on Google Earth imagery, whether it be satellite or aerial imagery from Google Earth. We can rely on our own hand measurements or site inspections, or we can rely on laser scan data or other data that allows us to determine accurate XY positions of various items that we may see in that video frame that we can use then with the linear perspective method to determine locations of that truck. In this case, if we go back a slide, we can see that in frame, there are a lot of telephone poles, we have buildings, we have some signs, mailbox, a lot of different unique features that have fixed XY locations that we can identify, many of which we can identify in Google Earth and then use in conjunction with these various frames to identify location of the truck. So how do we do that? Basically, we combine, in this case, we're going to use Google Earth imagery. We combine that in CAD along with the known path of the truck, and then we draw in lines of sight emanating from our camera position. So this is our laboratory here. We have a known camera location on the corner of our building. We have telephone poles. So this analysis, we're going to rely on those telephone poles that we saw on the far side of the road. This zoomed in image shows us 2 poles. We have 3 more poles out here further out that we can't see in this particular image, but that we do have captured in the image and in CAD. We draw a line of sight or a linear perspective line between each pole and the center of the camera. We also know from watching the video visually that the truck is in the right lane proceeding along the roadway. This is this orange path. Using those 2 pieces of information, we can now identify where these 2 lines cross. We have a position here where when we know the nose of the truck is overlapped with the pole in the image, that truck is going to be in this XY position. And similarly, when we have a frame where the nose of the truck is overlapping the first telephone pole, we know that in CAD, in the XY top view, this is going to be the position of that truck. So this is how we use the linear perspective method, along with the video and geometry or information from the area to determine positions of the truck. So what does that look like? So when I look here at one of the frames from our video, and again, a video is just a series of still images being played. When we look at this frame here, you can see that the nose of the truck, so the center of the nose where the Ford emblem would be, is in line with this telephone pole here with pole number 1. So at this position where the nose is in line with the pole, we know that the nose of that truck is going to be in the same line of sight as that telephone pole. And again, knowing that the path of the truck is moving along the street, we know that this position that we see here in this frame going back correlates to this intersection position right here in our aerial or top view CAD model. So again, this is how we're going to determine. We're going to do that for each each pole. We're going to identify the frame where the nose of that truck is in line with the pole, and use that to determine the positions and the frames where those positions occur for the video. So we still are missing one key piece of information. So what we've done right now is we've identified the position of this truck at various keyframes. But in order to do speed requires not only position, but it requires time. So how much time passed between those frames? And that's the next determination we need to make. This isn't always as easy or as straightforward as many people may think. Obviously, many videos are filmed at a constant frame rate, and that constant frame rate is oftentimes reported in the metadata that's associated with that file. But this can get an expert into a lot of trouble. Although oftentimes it is the case that a video is at constant frame rate and that the metadata is correct, that's not always the case. We have seen plenty of cases where the metadata is wrong. It reports an incorrect frame rate, or it reports a constant frame rate when in actuality the video might be at a variable frame rate. What that means is basically not every frame is being played for the same period of time, and that this constant frame rate that some experts may use in their analysis isn't going to be correct and is going to create inaccuracies and errors within their analysis. So here at Robson, there's a number of things we generally do when doing a video analysis to ensure that we have confidence in our frame rate. Visually, we can look at the frame. We can visually analyze it, looking for skips, jumps, or other things within the video that could give an indication of missed frames or variable frame rate. We can also validate if we have objects within the video that are moving at a known speed. We can use those to and back calculate to ensure that the frame rate that we believe the video to be at is indeed that frame rate. We also use here a program called Axon Investigate, used to be called Input ACE. This is a very special forensic software used for analyzing video. Axon being the makers of many of the police body cameras that we come across. And that can also delve further into the video file and give us a better idea if we're looking at a constant frame rate, if we're looking at a variable frame rate, and if it is a variable frame rate, what is the frame rate for each individual frame being played, so that we can take that into account in our analysis. The last thing that we try to do is, again, the larger the time span over which we do our analysis, the less that any individual frame rate error is going to affect that analysis. So what I'm saying there is basically, if I were to take frame 1 and frame 2 of a video and try to determine the speed of an object between just those two frames, obviously even any small error in frame rate between those two frames could lead to a fairly large error in my speed calculation. But if I now spread my analysis out over 10, 15, 20 frames, if there is some small frame rate error between a couple of those frames, obviously that error is going to translate into a very insignificant error when I'm taking a speed over that larger amount of time and larger number of frames. So again, we always try to take as many frames as possible and try to do multiple positions. Instead of just averaging from frame 1 to frame 20, we'll try to take intermediate positions as well and plot those in order to see whether or not there are any irregularities that would indicate an error either in our frame rate or positioning. So all that said, let's take a look at the results here for our first analysis. So we can see here on the plot, we have time on the X, distance on the Y, and we have our 5 positions plotted. And you can see that when we draw a straight line through those 5 points, the slope of that line is our speed. Again, this is distance versus time. And if you look at the slope, that represents distance divided by time, which is our speed. In this case, 43 feet per second, or about 29.5 miles per hour. So again, you can see that we have a very good fit. The straight line would indicate that the truck is moving at a constant speed. It isn't accelerating or decelerating. And you can see that the variability in data versus the curve fit is very tight. We have a very good R² fit or residual, leading us to have lots of confidence that both our frame rate and positioning are accurate in this case, and lead us to have high confidence in our speed determination. So that was our first analysis. We're now going to move on to a second method that we use. So we're going to do the same analysis, basically speed from video of the same video, but we're going to use another technique that we often use. This technique is called camera matching and reverse projection. In this case, we're going to use a commercially available software program called PhotoModeler. There are others on the market. PhotoModeler is one of the ones that we use here at Robson. And basically, PhotoModeler is going to use three-dimensional scan data of the area to backwards calculate parameters for the camera. So we're going to give it positional data from this laser scanning that we did of the area. And the software is going to determine the position of the camera, the focal length of the camera. If we have enough data points, we can also determine lens distortion of the camera. And all of those parameters are going to be calculated and then allow us to reverse project or project images back into the frame as seen through the lens of the camera. And then we can position those objects till they overlay on the actual objects seen in the video in order to determine their positions. I know that sounds really confusing, but I think once we lay it out here and go along, it'll make a lot of sense. So the first step is we take our three-dimensional scan data and we pick a number of control points, and we use that to basically solve for the camera. What does that look like? Well, once we're done, we can take that laser scan data, reverse project it back onto the frame that we have here from the video to take a look and see how well were we able to match our camera. So I'm going to go through these slides forward and reverse so you can kind of see the transitional effect. So this is the video frame that we see here unaltered. And then we're going to slowly overlay our laser scanned data, which is three-dimensional point data taken using, in this case, a Leica laser scanner. And we're going to overlay it. So now you can see that we're basically looking at laser scan data. And as we back up, we're looking back at the video frame. So you can see that we have a pretty good fit. Our telephone poles line up, our building here in the background, our sign in front of our lab. You can see that fences, road, everything seems to visually line up well. The software will also provide us with a mathematical representation of how well it was able to fit the data. But again, we always look at this visually to ensure that our visual fit is what we expect. Once we have this fit done, we can now take this information that we processed and determined for the camera, and we reverse project in data. In this case, we're going to take laser scan data of the truck in question, and we're going to take that laser scan truck, project it back into the image or back into the frames of the video, and we're going to move it around in three-dimensional space until it lines up with the positions we see in the video frames.
5 seconds here.
Sorry about that. So in this case, here's a frame. We get a zoom in of the truck here. And we're going to, this is already positioned, but again, if we were to reverse project our laser scan data of the truck in, if it were in the wrong position, it may appear over here or in front. And we're going to continue to move that laser scan data in three-dimensional space, reverse project it back into our image until we line it up with the actual image in the video. So in this case, you can see as I overlay, we can see the laser scan data now very, very closely matching and overlapping the image of the truck that we see in the video. So again, we do this for each position of interest. So we select certain key frames, we reverse project and move the data until we have a good match. And then just like with the first analysis, we will take those positions. In this case, we did 3 positions of the truck. And again, they appear to be linear, showing a constant speed. And in this case, we have a speed of 28.8. So if you remember, the original analysis we did using linear perspective was 29.5. using camera matching and reverse projection, we get a speed of 28.8. So again, pretty close speed using two different methods. There's one more twist I'm going to share with you here today, and that is oftentimes we don't get an original video. In fact, worst case, we get a video of a video. That's when somebody takes their video camera out or their cell phone, and they literally videotape the video playing on the computer screen or potentially the security camera server in order to capture that video. This can create issues, especially when it comes to video frame rate. We do need to take extra special care in these cases to ensure that the frame rate that the video camera that recorded the video is playing at or recording at isn't going to interfere with the original frame rate of the original video. So things we need to look at is the video over or under sampled, meaning is the frame rate of the original video higher or lower than the video camera used to record it? Was the video playing in real time on the computer screen that was playing it? Sometimes the computer playing a video may skip frames. It may be slow for any number of reasons where the playback has been slowed down. So again, there's ways that oftentimes there's information we can use to verify if it's playing in real time. And again, to ensure that we're not dropping frames or skipping. And oftentimes some of the information we use to do that are clocks. If we have a stained clock, which is a clock that is part of the video itself, or if we have a clock on the player that was captured as part of this video and video recording. Again, it's not that we can always do this analysis. Sometimes we do not have enough information, but oftentimes there is enough information that we can go back and verify so that we have confidence in the original frame rate or the frame rate that we're using in order to do these types of analyses. So again, in this case, we did just that. That same video that we saw earlier in the first two analyses, that was from our own video camera or security camera here at Robson. So we went ahead and took one of our cell phones and we recorded that video playing on our security server and then used that video of the video in order to do the same analyses we did in the first two. I'm only going to show you the linear perspective methodology used with this. Obviously, the camera matching method takes a lot longer since each frame now needs to be done individually to camera match because, again, we don't have a stationary camera. The camera recording this computer screen can be moving, shaking, so it becomes a much more time-intensive process, but the linear perspective still works in relatively the same manner as it did before. We basically take the truck in each frame. For instance, here in this frame, we can see the truck is again lined up with pole 1. We can take a look at the play time timestamp here. We can look at the stain timestamp in that individual frame. And again, we go about doing our analysis very similar to how we did the original analyses. Again, just with more care taken in our frame timing. So in this case, again, we have 5 positions. It is a linear fit that we have, and we came up with 29.3. So for those of us who are keeping track, our first analysis gave us 29.5. Our second one, I believe, was 28.8. And here on our third analyses, we have 29.3. So the question is, what was the actual speed of the truck? Well, lucky for us, we had a camera inside, and the truck was actually set on cruise control to a speed of 29 miles per hour. So although there can be slight variance in the speedometer of the truck itself, overall, I'd say that we have a pretty accurate analysis, very reasonable speed estimate from video for this truck going down in front of our lab. So that said, few more notes that I want to go through here before wrapping up. One, estimating error is always important in this type of analysis. Obviously, there's a few ways we do that. We can estimate our positional error by looking at the basically the resolution of the video and where that vehicle falls within the video. We can estimate, can we accurately position it within 1 or 2 pixels? What kind of dimension does a pixel represent in that area of the video, and use that to come up with estimates on our positional accuracy. Obviously, also take into account how accurate are the maps that we used, how accurate is Google Earth. We have some papers, obviously, that provide that type of information for us. The second method is, again, when we have multiple points, as we did in this analysis, and we do a linear or otherwise a polynomial regression, we can use those residuals to provide an estimate of individual point error. Interestingly, when we do those regressions, frame timing error also will show up as a positional error if we assume that the frame rate was correct when doing that plot. So it's really great because that allows us to basically look at the overall error, both from a frame timing and a positional standpoint, which is why I like when I do these analyses, I always like to do more than 2 points. I always like to do 4, 5, 6 points and plot them in order to get a good mathematical representation of the type of error that we're seeing. And then, of course, we can do independent validation studies, such as this one. We can do those specific to a video camera in question or an area in question. Or we can look for published papers that have done these types of analyses in the past to get a overall general error rate for these types of analyses. And then one final note, this is something I come across a lot, so I do like to discuss it quickly, and that's on the topic of lens distortion. So a lot of times, I believe there are a lot of people out there that believe that no analysis can be done unless lens distortion is first corrected. And that is not actually accurate. There are many types of analyses and many types of photogrammetry that do require lens distortion to be corrected prior to doing any analysis, but that does not hold true for absolutely everything. Great case in point, the linear perspective line of sight method that we used, both in the first case study here and then in the video study. That actually is not affected by lens distortion. And if you don't believe me, I'm going to prove it to you here in the next couple of slides. But again, when two images are on top of each other in an image, when we undistort that lens or use lens correction, we don't add pixels, we don't take away pixels. There's no way of taking those two objects and not having them still be on top of each other, whether the distortion is present or not. In addition, so when we do our camera matching, Photo Modeler, this is in our second case study, we use Photo Modeler and camera matching. Photo Modeler can correct for lens distortion on its own, given enough control points. But again, if we don't have enough control points and it can't correct for that lens distortion, it's simply going to report mathematically a higher error rate. And again, as long as we have an understanding of what that error rate is, it doesn't render the analysis incorrect just because we didn't correct for lens distortion. It simply means we have a higher error rate. And as long as we're okay with that error rate, obviously, we can still use that analysis. So just to give you, to show you what I was talking about here with lens distortion, on our left, we have a highly distorted fish-eyed photograph of a building. You can see in the bottom right here, we have two pedestrians standing. And here to the right is that same image after being corrected for lens distortion. Again, we can see our two pedestrians standing here on the right. If we zoom in, if we were interested in the position of this right pedestrian relative to this concrete column here, you can see that the center of her head is still in line with that concrete column, both in the distorted and the undistorted image. Again, when we apply lens correction is never going to take the position of this pedestrian and move it left or right relative to this pole. It can't add or delete pixels. It can only stretch and compress pixels. So with that, that is our presentation for today. I think we're actually perfectly on time here. If you guys have any questions, please feel free to ask now, or again, if you'd like, you can email as well.
Thank you so much, Marcus. I have a question.
Sure.
How much time does it take when you have to match each position between the cameras and the laser scan data? Like, how time consuming is that?
Yeah, so the initial matching where we take the overall laser scan data for the area and we come up with the original or the initial camera match, that process, again, there's the time to laser scan, process the laser scans, then pick the control points and do that. just the time for the matching process could be 1 to 2 hours. There's about an hour of laser scanning time, and then of course, any time on site to laser scan. In this case, between the laser scanning, processing, and matching, we probably had about 3 hours just to get to the point where we had the camera matched. Once we add the additional positions for the truck, you might be looking at another hour, hour and a half, maybe 2 hours to get the individual truck positions on top of that.
So the simple answer is it depends.
It depends. It always depends.
We just got this question. What type of video quality is required in order to get this type of data?
So same answer, it depends. If we can make out the object in question in the video and we have enough geometry in the video to use either for either method, basically the resolution of that video is simply going to go to the error rate. So the higher quality or the higher resolution the video, obviously the more accurate we can be in our speed estimates. Again, as we get grainier video, we can still come up with a speed estimate most times. But again, keep in mind that your error rate is likely going to go up with lower quality video.
That makes sense. Okay. Well, I think that is going to be our presentation for today. Thank you again, Marcus. Thank you, everybody who came. If you do have any questions or follow-ups, our contact info is on the screen. You can find us at robsonforensic.com, and we'll see you on the next one.
All right.